Elman sir, shall we start?
Okay,
Yeah, I think.
so good afternoon to everybody and welcome back. We have come to the end of the webinar. Today we had Dr. Srikanth, who is an associate professor in the Department of Chemistry at NIT Trichy. And he had his MSc and PhD from Cochin University of Science and Technology, Cochin. After PhD, Srikanth spent 4 years in ETH Zurich, Switzerland, in the Department of Chemistry and Applied Life Science before he joined NIT Trichy. Srikanth's research interests are coordination chemistry, chemistry of transition metals, and lanthanides, DNA binding and biological studies of metal complexes, corrosion chemistry, and engineering and molecular docking. Dr. Srikanth has guided over 4 PhD students and has published over 70 research papers in highly cited journals. I am happy to invite Dr. Srikanth to deliver his talk on pulse CPR and its application in inorganic chemistry. Over to you, Dr. Srikanth.
Thank you, sir. I'll just share the screen. I hope it is visible now.
Yeah, yes.
Thank you very much for inviting me and also reminding me to a very good old topic which I used to work quite a long back. So today my lectures is mostly based on kind of old work because inorganic applications is something which people rather very rarely do for pulse CPR these days. And pulse CPR itself have gone from regular characterization techniques, it has moved into LDOR, distance measurements, etc., into a completely different regime. So pulse CPR, I'm going to mostly focus on how it is being useful in inorganic chemistry and how it as a tool it is being used in the inorganic chemistry. So a lot of spin dynamics is involved when it comes to the pulse CPR spectroscopy. We already had a wonderful lecture from Professor Bhatt as well as regarding the fundamentals. We had a lecture from Pratap Chandra Group also. So these two regarding the continuous wave EPR, I think everyone already might have got some idea about how continuous wave EPR spectroscopy work out. However, I'm going to have a small recap about that. At the same time, avoiding a lot of equations and theoretical components, my lecture will mostly focus only on the application part, how data can be derived or how we can understand the spectra. The problem is you might think what is so difficult in if you have a spectra, it's like any other spectroscopy. I can directly derive the spectra from looking at it. But unfortunately, EPR is even the continuous wave EPR is not that straightforward, so that we can just go into and take data out of it and calculate. That way it was never possible. So the things started way back. Perhaps all the EPR people in older days were always used to be very much proud that the year 1944, a year before NMR was officially invented, Zayevsky in Kazan State University invented the continuous wave spectra. He observed the spectra in cupric chloride, and this is the first spectra observed in much lower magnetic field and a much lower microwave field. Cupric chloride spectra was observed by Zayevsky, and later with a couple of experiments, one by Richard Bloom, who invented electron spin echo in sodium, the electron trapped in sodium ammonia, and also Mims, who observed a modulation in the echo amplitude. So that means this is an echo, and the amplitude modulation in that was observed in Syria-topped systems caused by tungsten. as an element. So this modulation was nuclear modulation, which was later only identified as a nuclear modulation, paved to the entire nuclear spectroscopy in EPR technology as a whole. So until that time, it was continuous wave EPR was only like you have to take the spectra, find out the G value, and average, look for the crystal deficiencies or look for the ground state of the inorganic complex you have prepared, etc. But after these inventions, this has gone to a little bit more elaborate level with the hyperfine couplings and electronic ground state and what nuclei are surrounding the metal sender. All these things become more interesting. And we can obviously not forget the contributions from Professor Schweiger, who was also my supervisor during that period, who has comprehended the entire work of Pulse EPR in his textbook, which is a very classic textbook known as Principles of Pulse Electron Dynamic Resonance, authored by Arthur Schweiger and Gunnar Eschke. Professor Schweiger has approached the EPR or exploited the Pulse EPR techniques completely into the real-time systems. To the extent that you're starting from very simple inorganic complexes, organometallic systems, biological systems. So I think that was one wonderful type of pattern he has produced. He has invented many experiments. So to say, one or two experiments I will just show in the end. We have also done some real samples. So this is on one aspect. These he always used to say that these are crazy experiments because they took time. On the other hand, the results are magnificent. And when they are applied to real-time systems, we will always confront with how to elucidate the data and how to get the data out of it. So paramagnetic compounds generally are not many around us. Like free radicals are there, triplet states are there, point defects are there, semiconductors or transition metal ions are rarer. And on the other hand, we have almost 90% or 95% of the compounds are diamagnetic in nature. Hence, NMR has grown into a complete technique. And with almost everything is possible. If you have a machine with you, an NMR machine with you, you don't really need any other technique. In that level, it has grown in over last half a century time. So how do you handle diamagnetic compounds? This is something which people are more interested in EPR spectroscopy now. If you look for works contained of Professor Goldfrapp or people like Stefan Stoll and over the entire work, you see that the spin labeling has grown, or spin labeling techniques have got a lot of interest in distance measurements, in symmetry, electronic structure, local geometric structures, kinetics, dynamics, and excited state analysis. So if you have to compare NMR versus EPR, you have a very simple slide. This slide has been borrowed from Professor Schweiger because he always used to show it in the beginning of his every lecture. Even though the aromatic ratio of electron is almost 657 times larger to that of proton, EPR has its own difficulties to work with the instrumentation side. On the side of sensitivities, sensitivity wise it is very high, but you don't really require larger samples like NMR do in the higher measurements. But we have issues obviously concerning to the orientation selectivity, because NMR we can easily derive most of the data from the fast motion regime, where you can measure it at the room temperature itself, where EPR you cannot measure or get some information properly unless otherwise you have properly oriented samples like a single crystal or oriented or isolated single spin systems available to us. Most of the systems available to us are powder. Powder in the sense that it is either powdered and diluted paramagnetic compounds or dissolved paramagnetic compounds which are lowered in temperature and made into a powder, in the sense that they are called as frozen solution or glass. So this aspect, when it is coming to that point, NMR almost all the time is measured at room temperature, where we have, due to this orientation selectivity issues and G-value separations, this we will discuss later. And obviously other things like zero field splitting or strain assigned to the G values, we measure at lower temperatures. And when it is coming to NMR, we will just have very high sensitive, high resolution without any issues. We have a machine, we have standard format to work on it. We can directly get not much of an issue. But on the other side, we have a lot of EPR techniques available, lot of EPR machines available, different magnetic fields, different microwave frequencies, different techniques. This has to be applied depending upon the application you are functioning in. So generally speaking, we always, whenever even this we follow now, we start at some point with what application we are aiming at. We measure some instrumentations, and then you have the spectral simulations combined with the DFT calculations, and it is an iterative technique. You go in, go out, refine your experiment, find out the DFT parameters, and then again you go back and again reiterate the entire thing over and over again. At times when we have a start with single crystal X-ray, it is the best to start for DFT calculations. Even otherwise, we have to optimize the geometry, and we can arrive at most of the time good solved problems. So majority of the EPR, when it is coming to a continuous wave, when it is coming to pulse systems, we call it as field swept EPR. It is a continuous wave. It looks like a continuous wave, but in continuous wave, due to the modulation effects and all, normally you get a differentiated spectra, and here always you get an integrated spectra. So this is an axial system, which normally people will recognize immediately. If you differentiate this signal, this will look like a normal EPR signal, which is axial in nature. So from here, first point of recording any spectra in a pulse EPR is to record an entire field swept EPR, so see how the G values are spread across, and then you have to decide your experiments accordingly. So these two techniques are generally, Endor as well as ESIM, are generally used in the applications of inorganic chemistry or structural applications. These are mostly used. Spin distances and molecular motions are mostly used in material science applications. So my talk today mostly is going to focus on these techniques, where as the title goes, it has to be inorganic characterization. So mostly I'm only going to focus on these two main techniques called as Endor and ESIM, along with the field swept techniques. So to start with a little bit of the theory, so those who are very much familiar with the NMR spectroscopy's theory part, as well as the spin dynamics concerned to the NMR, people are already familiar with these interactions. So the entire nuclear spin Hamiltonian, this is the nuclear spin Hamiltonian, this is not electron Hamiltonian. So the nuclear spin Hamiltonian is constituting of the nuclear Riemann interaction plus hyperfine interaction plus nuclear quadrupolar interaction. So here in the case of NMR, you are not much worried about these G values, unless otherwise you are worried, of course, when you want to measure as rare nuclei other than carbon-13 or proton, to how to set the signal to a maximum level, etc. Other than that, but when it comes to measurement of nuclei using EPR spectroscopy, you have to be aware where the nuclear Riemann comes, and obviously these two are directly proportional to the magnetic field. So the more the field are, the more better resolution is, and more better spectra you will observe. And more than that, people are interested in this part in the middle of it, which is A, This is what we normally record it as hyperfine coupling. And one more salient feature of EPR spectroscopy is that most of the times, if you perform the experiment nicely, you can get quadrupolar information from nitrogen-like elements. So magnetic nuclei and their interactions with the unpaired electron are three in nature. One is that unpaired electron interacts with the nuclei with the external magnetic field applied to it. Hyperfine interaction is a magnetic interaction of the nucleus with the field due to the electron spin. So the electron spin interacting with the nuclear spin will produce the hyperfine interaction. Nuclear spin Zeeman interaction, on the other hand, is the magnetic interaction of the external field with the nuclei, and electron Zeeman, which is obviously the origin of the entire EPR spectra, is the magnetic interaction with the external applied magnetic field and the unpaired electron present in the system. And in the quadrupolar interaction, on the other hand, is the electrical interaction between non-spherical nuclei in the inhomogeneous electrical field. This is an internal interaction. This is an interaction between the coupled nuclei, and this is an interaction between the nuclei and the external magnetic field, hence constituting the entire nuclear Zeeman equation. Whereas the origin of the spectra comes from this very simple equation, which is in fact looks only simple, derived from very complicated calculations. So delta E is equal to H2, obviously GE beta E B naught. This is the same equation we generally teach for the magnetic resonance NMR spectroscopy lectures also. H nu is equal to G, where it is Gn beta n, and B naught obviously is the external magnetic field which is applied. And the Zeeman effect causes the energy levels to split into two if it is a MS plus or minus half system, and only plus or minus one transitions are observed for allowed EPR transition. Of course, there are forbidden EPR transitions also, but however, in direct EPR observations, most of us are only worried about allowed transitions. We look for only allowed transitions, except for ASIM, where forbidden transitions are invoked back for the signal enhancement, as well for the sake of the signal enhancement. So the splitting between the two energy levels are called electron Zeeman interaction. That means when you place an unpaired electron in an external magnetic field, that unpaired electron will cause a spin splitting, and therefore the two different states are observed. These are fundamentals which you have Professor has already covered in his previous lecture. So this is electron Zeeman interaction is directly proportional to the magnitude of B naught, that is the external magnetic field. Hence, we always have different type of spectrometers available to us depending upon the microwave frequency and depending upon the magnetic field which is employed. So major of the commercial instruments are available in these four categories. Above this high field EPR, we require certain high field techniques which has to be built in the laboratory. S-band is like our microwave oven frequency approximately. X-band is the most popular frequency because it is almost cheaper also and widespread available as well. Q-band is while working in EGH, we have mostly used Q-band because it is one of intermediate frequency which is perfect for resolution in both electron Zeeman as well as nuclear hyperfine interactions. So 35 gigahertz was kind of sort of our favorite frequency over a longer period of time. And W band, obviously, when you are looking for here, you see, you obviously get a lot of G value resolution. The spectra is spread over a huge period, and the spectra is much well resolved. However, at the expense of some other data, that means some other data are lost or hidden or buried under the line width when you go for from a lower frequency to a higher frequency as far as EPR is concerned. So electron Zeeman increases in this direction, but what happens is the proportionately the nuclear Zeeman effect or nuclear hyperfine interactions are a constant. So since that the hyperfine couplings are constant, this increase will cause the loss of data, or they are buried under the line width. So you cannot really tell, like in NMR, you go to a high field, you get a much high resolved spectra. You will never get that. Very highly resolved spectra are obviously observed at the lower frequencies, and at high frequencies, highly G-resolved spectra are observed. So you can see that I'll show you some different frequency spectra in few minutes. So so that you can assess by yourself how the splittings are they're present in S band or in X band, and how the splittings are absent in higher frequencies. So pulse EPR also looks for a set of high resolution EPR techniques to determine the local structure around a spin center. So the basic spin center in our molecule generally is the unpaired electron, which is generally kept as one unpaired electron. People are very safe when they handle one unpaired electron system. Because the more number of unpaired electrons are, we have other issues coming to it, like couplings, or you have zero field splitting, and corresponding to every unpaired electron system, when unpaired electron system, there is different EPR transitions possible. So like in the case of manganese, where you complicate it enough that it has different 4 different transitions possible, and from that magnetic the 5x2 system or 3x2 systems, they get immediately highly complicated. Whereas 1x2 system is very simple to handle with, very simple to interpret and understand with. So I think almost throughout the lecture, I will stick on to a 1x2 system. So in a continuous wave EPR, what it does is it looks only in the middle, the electron, and they are mostly probably at an immediate up to a maximum of 2 to 2.5 angstrom limit. Which is maybe maximum of this example is for firing center. If you can very clearly see, there are 4 nitrogens corresponding to it. So the electron bonded to 4 of the nitrogen atoms. So the electron is obviously on a metal, and correspondingly there are other hydrogens which are shown, other nitrogens which are shown far away. Obviously they interact with this unpaired electron, but we can't see in a continuous wave EPR system. So a metal center is very strong. As far as a continuous wave EPR is concerned, metal center is most important. It is being focused. Ligands are, yes, they are important, but immediate ligands are important. So only strongly coupled magnetic nuclei can be observed as far as continuous wave EPR is concerned. I mean, if at all you observe it in the spectra. Most of the time, what happens is that you will only observe the unpaired electron signal. You don't observe anything else, but it does not mean that other interactions are not there. Other interactions are always present, and they go under the line width, and that for that purpose you require pulse EPR techniques to derivatize other knowledge. So in the case of pulse EPR, when you go from immediate surroundings, you leave this regime, you move out, and as this big larger dark circle is shown, you can see the ligands in the first and the second coordination sphere, hydrogens bonding interactions, distances to the other spin centers. This is what is being focused most of the time in the pulse EPR. So distance measurements means, for example, you have a huge protein, which is a bimetallic protein. So you have one protein center over here, another protein center over at a distance. You can find out a distance between these 2 unpaired electrons present in these 2 different protein centers by means of an experiment called as DEER, D-E-E-R. And for as far as these secondary and tertiary ligands are concerned, we have to go for nuclear measurements based on the pulse EPR techniques. So that is how it is set as far as the experiments are concerned. So So the first and primemost thing whenever we look for an EPR spectra is called as the G factor. G factor comes from this very same equation which we have already, I think we have already discussed in the past lecture also. This may have come across. It is also called as Landau splitting factor, or G is very characteristic of the sample. So G is like, you looking at the G value, you cannot really say what nuclei you are having. But sometimes looking at the line shape, yes, you can predict that, okay, I have a copper, I have a vanadium, I have iron 2, iron 3, I have cobalt. This, yes, this is possible to tell. But however, real systems really deviate a lot. So unpaired electron has a G value. From the unpaired electron G value, that means the pure electron without any surroundings have a particular G value which has been estimated like long back in the beginning of the last century itself. If they have, physics people have found out the G value and the charge of the electrons, etc. So these are known constants over a period of time. What happens when the unpaired electron is present in a metal or it is present in an organic radical? Then what happens is the real system tend to deviate due to three main factors. One is called as spin orbit coupling. Other one is called as crystal field splitting in complexes. And third one is, it depends on where your unpaired electron resides on. Is it residing on a sigma orbital? Is it residing on a pi orbital? Is it residing on a delocalized pi orbital? Or is it sitting in an aromatic system? So they decide the deviations, and most possibly this is the vector of this electron Zeeman. So you have magnetic field acting upon the G values. So the G values, obviously, as you can see, that it is a 3x3 matrix. That means it operates in all the three directions in the 360-degree sphere. So whenever you are representing G values, you represent it as a sphere. And whenever you want to pick an orientation, you have to pick it accordingly, because whenever each of the Bx, By, Bz acting on it, so it is like if you remember your matrix multiplication, this is spin over here. The spin is this is multiplied, and then the magnetic field is multiplied. If the multiplication matrix is expanded, you will have some idea like how the entire spin system is responding, or spin system is acting when they are placed in the external magnetic field. So the combined effect of these interactions removes the orbital degeneracy. And what happens when the orbital degeneracy is removed? The energy levels of most of the transition metal ions are already in a crystal field splitting. So already the crystal field splitting has removed the orbital degeneracy in the d orbitals. So leaving non-degenerate ground states often with a zero orbital angular momentum, or we generally call it as the angular momentum. Orbital angular momentum is quenched. So when this is happening, the G value deviates from the normal values. So organic radicals, the deviation is less than 1%. So, but for coordination complexes, the variation is very huge. So when you compare an organic spectra and a EPR spectra of an organic radical, when you compare or superimpose it with the copper spectra, the width of the spectra itself may take you to a surprise that organic spectra are so small, but at the same time since they are very small with a very sharp line width, their nuclear frequencies are highly observed in organic radical spectra. So radical chemistry is much more interesting, much more easy, and much more straightforward. And when it is coming to inorganic chemistry, nothing is straightforward, nothing is simple. All has become very complicated, and you have to always go for the difficult method to elucidate the data from the spectra. So for organic radicals, since the deviation is smaller, it is easier. And the G tensor, most of the time what happens is the G tensor in most of the time when you measure the spectra in room temperature, all G tensors undergo a tumbling motion. That means they rotate. The rotational energy levels, as we have studied in microwave spectroscopy, the rotational energy levels, when they undergo tumbling, that means they are called as fast motion regime, which is room temperature itself. The solution, the high symmetry of the G is observed. That means, irrespective of the orientation, all the G values are aligned together and they appear at a single spot. And this spectra is generally called as isotropic spectra. And this is directly opposite when you cool down the system. That means you go from a single orientation or averaged out orientation to powder type spectra. That means when you have a solution of inorganic complex and then you cool it down, you have all the orientations frozen. Let us say at the liquid nitrogen temperature, which is around 110 K or 105 K, approximately that temperature when you are measuring it. You have a completely frozen solution and all the spins are frozen at some or other orientations. Your entire matrix will get activated and you will get an entire spectra with all orientations possible, summed up to have a non-isotropic spectra. People tend to call it as rhombic spectra or axial spectra or reverse axial spectra in most of the time, depending upon how much of the orbital angular momentum is quenched, what is their crystal field splitting data, and looking at the shape of it, looking at whether it is axial or reverse axial or rhombic, you can sometimes predict the ground state of the nuclei, as well as even tell that what nuclei we are working on. So nuclear Zeeman interactions are very interesting, yes, to an extent, but we have to know the nuclear Zeeman interaction. For example, what place or at least what is the frequency at which proton will resonate at an X-band frequency. For such calculations, the nuclear Zeeman interactions or knowledge of nuclear Zeeman interactions are very important. So most of this slide is meant for that. You can see that most of the important nuclei are listed over here. The spins are listed over here. Here we can have multiple spins. For example, copper is a 3/2 system. Manganese is a 5/2. I is equal to 5/2 system. Cobalt is I is equal to 7/2 system. Nitrogen 14 is I is equal to 1 system. Doesn't matter for us as long as we are working on a S is equal to 1/2. That makes our life much more easier. But in all the other cases, as you can see, the nuclear G values are very small. But when you are converting the entire thing into frequency wise, at an X-band frequency of 9.8 gigahertz, your proton will resonate. Or if you are measuring an NMR spectra on the EPR spectra, which we call it as Endor spectroscopy, when you are measuring that at 9.58 gigahertz, your proton is going to resonate more or less at a 14.9 gigahertz or approximately 15 megahertz, which is very small. As and when you go from here to from X-band frequency to Q-band frequency, approximately this will elevate from 15 megahertz to 50 megahertz. So we have a little bit of a higher value for the nuclear Zeeman frequency. And then comes the hyperfine interaction, because we will discuss about how hyperfine manifests in the nuclear frequencies. Hyperfine is our chemical shift. If you exactly want to talk like on NMR terms, NMR we speak about chemical shift. If we do not have, we never had chemical shift, NMR was, I don't know for what use NMR we could have had. But we talk always on chemical shift, and chemical shift is like chemical shift, no matter in what frequency you are recording the NMR spectroscopy. We almost average out the chemical shift by means of having a factor multiplied and divide onto it, and we have proton always resonate at the same place. Where aromatic proton, if it is an aromatic proton, your expectancy is at a place. If it is a methyl group proton attached to OCS3, that has a resonance place. We know it, but this again we cannot do it over here. Each place this tends to change, and we have to always find out where it comes. So always an EPR scientist should know what are the spins and what are the percentage of the abundance, their nuclear G values with respect to this. Once you have it using this equation, we can very easily calculate the absorption frequencies. So the total spin, this is a total spin Hamiltonian, where we have, this is the EPR, electron Zeeman Hamiltonian. This is the total Hamiltonian for the nuclear Zeeman, and this is for the quadrupolar interactions, where I have skipped the nuclear Zeeman effect. So this is the hyperfine interaction. This is the hyperfine interaction. Again, there is a small difference between these two hyperfine interactions. One is isotropic hyperfine interaction, and the other one is called anisotropic hyperfine interaction. Considering the fact that most of the time we are having isotropic hyperfine interactions in a typical system of G, S is equal to 1 by 2, I is equal to 1 by 2. First, this is the electron Zeeman interaction. So the electron, unpaired electron, will split into the magnetic field into two, and each of these levels are split into two by means of the nuclear Zeeman. These are also even, but when it is coming to this, the unpaired interaction of the unpaired electron with the spin of the internal field of this along with the internal field of these two levels, then cause a different type of splitting here, which are non-even. So what happens is, this produces allowed transitions, and this produces also forbidden transitions. And we are looking for only allowed transitions here. These two allowed transitions exist. These are obviously forbidden transitions, which are not shown in this diagram. So if you want to measure it, if you are having a technique to measure this area, that means if you are sweeping the field or sweeping the frequency here, the nuclei under resonance, and or using some technique, which I am not going to tell what technique now. If you are doing that, the center of it will be your nuclear frequency as discussed here. Let us say, imagine we have recorded it at 9.8 gigahertz. You are looking at a proton. So center of it is 14.8 megahertz. And on the other hand, one is shifted downfield, the other one is shifted upfield with a distance, and the center being the original microwave original nuclear frequency, which is a Larmor precision frequency. This distance is measured out and is represented as the hyperfine coupling constant. The more the distance is, more closer the nuclei is to the unpaired electron center. The shorter this is, we have the longer the distance between the unpaired electron and the particular nuclei. If you have a quantum mechanical model by means of DFT calculations or so, if you are developing such a quantum mechanical model, we can even find out the distances between the unpaired electron as well as the nuclear, and you can even arrive at a bonding or nature of the bonding, looking at the hyperfine coupling values. Since this is isotropic hyperfine coupling, that means this is evenly split, we do not have much problem. So center of it is nu, that is the Larmor precision frequency. Split by A is the system which is very perfect, or we call it as weak coupling system, or system with which is having a lower than coupling lower than the Larmor precision frequency, which is generally called as weak coupling. There are other cases also. When strong coupling exists, what happens? When intermediate coupling, that means what happens when the coupling constant is equal to that of Larmor precision frequency? Will you get it in the center? No, that is also again never the case. We will see these different spectra ahead. So this is how the spin Hamiltonian works out. I'm not going into any of the technical details of the spin spin dynamics. For those who are very much interested in the spin dynamics, they can refer to a textbook which is very classical by Malcolm Levitt. The book name itself is Spin Dynamics. It's a wonderful textbook, but a lot of mathematics and physics involved in it. You will not find any chemistry in that. Hyperfine coupling, when it comes to hyperfine coupling, this is our star of the day. You have, whenever we are discussing EPR spectroscopy, this is what something which always we are looking for. So I remember way back when I was doing PhD also, when you get a spectra, Guru sir used to ask, he said, coupling visible, hyperfine coupling and super hyperfine couplings are visible in the spectra. Some of them yes, some of them no. He is always happy to see that a well-resolved spectra is obtained. If it is a copper complex with a G parallel and a G perpendicular and a well-refined G parallel with 2 nitrogen on it, which is producing around 5 lines per G parallel lines. Those who have recorded an EPR spectra, they will know the pleasure of seeing such a spectra. And of course, those days we used to get in huge chart papers. Using scale and pencil, you draw this and then derive the entire data out of it, looking at the standard and the shift. And you have to do a lot of handwork to get it. When I moved to ETH, it was much more easier because we used to get digital data and we used to simulate the spectra using available simulation programs, which are now worldwide available online. So hyperfine coupling is something which is very interesting. We have 2 terms for hyperfine couplings. That is, one is AISO, known as Fermi contact interaction terms or Fermi contact coupling. This is in an interaction due to a very small but finite probability of finding the unpaired electron in the position of the s orbital. So this is the s orbital contribution of the nuclei towards the coupling. So this is major, and when it is when continuous wave experiments are done, mostly we can only derive the AISO or the isotopic hyperfine coupling. But there is another term for isotopic hyperfine coupling. This is anisotropy. Anisotropy depends upon the positioning of the nuclei with respect to the electron. The entire thing is the orientation in the space. So when the orientation in the space is random of the nuclei and the orientations are random, electron is oriented in some direction, the nuclei is oriented in, the nuclear energy levels are oriented in some other direction, the electron spin and the nuclear spin are related with a particular tensor called T, which is called as dipolar hyperfine matrix, which is also you have to take it out with the eigenvalues. They have 2 terms for it. If it is axial tensor, just don't worry about it. It is just, please remember that the hyperfine coupling will look like a non-even value. That means you might have more than one value for hyperfine coupling with the same nuclei interacting with the same electron. It gives you spatial information. That is the primary thing. Not only distance information, or it also gives you something called theta, which is how much angle it tends in the space with respect to the unpaired electron. So based on that, we have 3 regimes for couplings. One is called weak coupling, and the other one is called intermediate coupling, and the third one is called strong coupling interactions. Hyperfine values, when the B naught is larger than the hyperfine coupling value, we call it as the weak coupling regime. When the external magnetic field is equal to the hyperfine coupling value, we call it as intermediate coupling. And the external magnetic field is lesser than the hyperfine coupling, then it is called as strong coupling. In all the 3 different cases, we have different type of line appearances. This is a very rare occurrence. Most of our systems fall into this category, and rarely systems fall into the strong coupling category. Nuclear frequencies are seen in pulse EPR using powder spectra almost all the time, because when it is powder spectra, your single sender powder will elaborate the single sender and all possible orientations appear. This I will make it clear in another slide. This looks a little complicated over here. In both regimes, only thing is that this slide is meant to tell we are ignoring the intermediate coupling. Is very rare occurrences. Decoupling regime, we have a regular two different axial spectra. That means when you have seen here, for example, this was a perfect split as far as AISO is concerned. But this, each of it is, remember, each of it being axial. That is the case. This is the result. So you have one middle and two centers. One is called A parallel, another one is called A perpendicular. When it comes to the anisotropic hyperfine coupling value, this is quite this becomes more complicated. What is the center of the spectra? Center of the spectra here is the nuclear frequency split by the hyperfine coupling. That means you have AISO here, you have A parallel, A perpendicular in two different cases over here. The center is always the nuclear frequency. So you can read out. Just measure the distance, peak to peak distance, peak to peak distance, peak to peak distance will be your hyperfine coupling value. But what happens when it is strong coupling case? The center of it becomes center of it becomes half of the hyperfine coupling split by 2 times omega or 2 times nu. So the distance between the lines are 2 nu I, and the center of it always being the half of the hyperfine coupling. This gives a totally different type of splitting in the case of strong coupling regimes. Normally this is not observed. This is our favorite because we almost all general systems also work on this. So decoupling regime is more well studied, so to say, or rarely we can see the strong coupling cases emerge. So the G-value anisotropy is defined based on the entire orientation selectivity. So when it is coming to that, as recorded, you see the continuous wave EPR spectra is generally recorded like this. If it is seen recorded like this, this is the pulse EPR data, and with much more resolution, what happens is each of the places are much more resolved. But we do not know, unfortunately, they have buried under the unresolved splittings are buried under the language, hyperfine coupling to magnetic nuclei or coupling to entire other electron spins, all are buried under here. When you get this spectra, you have no idea what is inside. So the entire thing is data. How we have to solve the data out of it, you have to go for pulse APR techniques. Otherwise, you will end up only in recording 3 G values, G1, G2 and G3. So this is an example of 2 different fields. This is an S-band spectrum of a rhodium complex, which was long back recorded. You can see that it fits well with these simulation values. 2 nitrogens, 1 rhodium and 2 different protons. This fits very well. And when you move from S-band frequency to Q-band frequency, the entire data is gone under the line width. You have very clearly, here you have only 1 G value, but instead of 1 G value, the same spectra now has 3 G values, because this G ISO, so-called G ISO, is now split into 3 properly at the W-band frequency, which is around 10 times frequency or more than 10 times frequency of this, where this is recorded. But unfortunately, all this data which is derived from here is lost, or it is not lost. You cannot see it directly. So that is the difference between 2 different field effect in the case of a continuous wave EPR. So when you compare CW EPR with pulse EPR, continuous excitation is required in CW EPR. We require relatively lower microwave to operate in the lower microwave powers. It is an absorption spectroscopic phenomenon, and it measures a steady state response. So all these technical terms, for those who have completely understood the NMR spectroscopy, these technical terms are repeat here and there. They are the same. Only sometimes notations change, but the technical terms never changes. So measures a steady state response during the excitation. And however, CWAPR is most of the time is lowly resolved. In the other hand, pulse EPR has pulse excitation. So pulse excitation, as the name goes, it requires very high microwave power at a very short period of time, and it is obviously is an emission spectroscopy. and it measures the transient response after excitation is happened, and we are interested after excitation what happens to the system. So we are looking at the relaxation phenomena, etc., and often it is high resolution. So it's a small thing is how to prepare samples for EPR spectroscopy. We require very high quality sample tube. Before we go into any of the spectral measurement, we should know what is the OD and ID, inner and outer diameters of the EPR sample tubes. Because if you are measuring in S band, in X band, in Q band, in W band, you require different sample tubes. That is one major problem with EPR spectroscopy. As and when you go high in the field, your sample tube size goes down considerably. And generally 1 mm sample tube will go down to even 0.01 mm sample tube, and even if you are measuring DR, it goes down to micrometers. So it is just very small, and when you select the dilution also, you have to be very careful. If it is too concentrated, you will end up into broadened spectra. You do not really want to concentrate your sample with a lot of spins around. And if it is too dilute, you will not get enough signal. So you should approximately go for 0.5 to 1 millimolar samples will be very good, giving you fairly good resolution and fairly good signals. And when you go for measurement, you have to look for a few things. One is oxygen, which is you never want in the solution. You have to deoxygenate it because oxygen itself is having a signal. So oxygen sensitive samples, you have to have this, make sure that dissolved oxygen is removed. You have to avoid paramagnetic impurities. You should make sure that the quartz you use for the silicon tube should be devoid of any signals. And you should also make sure that there are no aggregations. And of course, the dielectric constant of the solvent is also problematic. That is the case. The worst of the solvent is liquid water. The best of the solvent is obviously organic solvents, which are only carbonaceous solvents. If you take hexane, for example, benzene, for example, beautiful. They form a very nice glass when you are frozen this entire system. But unfortunately, we know that most of our real samples don't dissolve in hexane or in benzene. So most of the people choose to have like ethanol or methanol or a mixture of chloroform, dichloromethane, ethanol, methanol, just that to manage the dielectric constant, not too much watery, not too much on the lower side. And most of the measurement techniques in pulse, when it comes to pulse EPR, the measurement is always almost all the time done in a temperature between 5 to 20 Kelvin. So that means you cannot perform an experiment at liquid nitrogen even. You will require liquid helium temperatures for that. So irradiation of such samples will reorient the spins and make us ready for the experiments. And here comes the orientation selectivity of different G matrices. This shows generally how 3 different or 4 different category of spectra we get normally when we have inorganic samples. One is isotropic spectra, as I have given the spectra also here. It is very simple. You have only one G value out of it. And there are 2 different type of axial spectra. We call it as first a G perpendicular and then comes the G parallel. We call it as reverse axial. And when it is first G parallel, then G perpendicular, we call it as axial spectra. And then there are 3 G values completely resolved in 3 different orientations. What is given in this spear ball is that the selectivity of the spins or how the spins are concentrated. For example, if you look here, isotropic spectra, the spins are distributed across the entire sphere. In the axial spectra, the electron spins here, for example, in this perpendicular region, they are more focused in the XY plane. In the G parallel region, they are more focused on the Z plane. So depending upon that, where do you choose? Here, for example, this is shown in the intermediate place. where you have spins not in the axis, not in the plane. It is somewhere in between the axis and the plane. So all orientations exist here. Here there are some particular orientations. When on on the pulse EPR terms, we call extreme end of the spectra as single crystal orientations. That means you have very focused spin orientations in this ends. Unfortunately, we have less signal strength over here. Where maximum signal strength is there, this is the middle of the spectra. Middle of the spectra always have maximum signal strength. This has all orientations. But that is now no advantage for us, because when you look for a pulse EPR data, it is orientationally dependent. That means if you measure here, you get one data. If you measure here, you get another data. You have to have at least 5 or 6 positions in between to club the entire data together to have a assessment of what is happening in your particular system. So orientation, this is much more better example. This is an example of cobalt complex, where in lower field it is in X band, in Q band, in W band it is split like that, and the same, it is exactly the same. Just to elaborate how the orientational selectivity goes from here to here, how it is focused. So for example, if you measure over here, the spins are more focused into one of the axes, and this is more good for us. And that we get single crystal like spectra when you record here. The most unfortunate part is signal intensity is going to be very less in this region. Then comes our star, free induction decay, because the NMR people had it so easy because their FID is very long. The problem with EPR people is that their FIDs are very short. As a general rule of thumb, FIDs last as long as the pulse length lasts. As a general rule of thumb, it's not always, maybe plus or minus. But the pulse length here we have to obviously use very stronger pulses with a shorter pulse length, because a stronger pulse with a strong and long pulses will destroy the cavity. We cannot use it, will heat up the cavity. So you cannot really use a NMR long pulse into an EPR spectrometer. Obviously, that instrumentation difficulties are there. So most of the time, like 90-degree pulses and all are very small and short and sharp pulses. So if you in NMR, it's easy. You apply one pulse, you have a huge FID, just record the FID entirely, and then Fourier transform it, you have your NMR spectrum. Here you really don't have that luxury, because we have what we are using in NMR EPR spectrometer is something called as a resonator, and the resonator itself has a ringing, and the resonator ringing and the cavity, entire thing, tuning, all these things added together, and you are hitting the entire system with the microwave pulse. All these things will bring out something called as a dead time. So dead time is a time after the pulses during which the power levels are too high to open a sensitive receiver. If you open the receiver at that time, your receiver is gone case. So you will just end up frying the receiver. Nothing happens. You will not get a signal. So it is not possible to open the receiver at least up to 100 nanoseconds after the pulse is applied. So generally speaking, you have a 100 nanosecond delay time after the pulse is pulse happens and an FID is recorded. But what happens, as you can see, FID started to evolve immediately after the pulsing. This is the NMR principle. This is the same in EPR also. You hit the molecule, the z-axis, you hit it to the XY plane. Your record observation is from here, because we are observing in the laboratory frame. The spin are spread across, and then they tumble back to here. This is what is recorded as an FID in NMR. So the spin processes with different frequencies with the dephasing, and they try to relax back. You are recording your NMR spectra. Here what happens is that You can only open the receiver. That means you can only start the detector at a point of 100 nanoseconds. By that time, your FID is almost completely over. You don't have anything to left out. The bigger the pulses, the same problem happens. As long as huge pulses exist, your huge FID can be seen. And of course, let us say like 500 nanosecond long pulse is applied. You can spare a 100 nanoseconds and then you can record. Obviously, what happens is there is a lot of error in the recording. So generally, FID detected data also has its own difficulties. So pulse EPR, nobody measures a continuous EPR like spectra. People will first record a CW EPR, look at it, and then go for pulse measurement. So this problem always there. We don't get a FID. So what to do? That was a problem. So then Richard Bloom earlier itself have invented this nuclear echo, and MIMS have also invented the spin echo, and combined these two, Erwin Hahn has invented a 2-pulse echo sequence. That means instead of 1 pulse FID, if you are having this echo sequencing is also there in advanced NMR experiments. Instead of 1 pulse FID, 1 pulse followed by FID recording, you use 2 pulse, a pi pulse, a pi by 2 pulse, and followed by a pi pulse, and then wait for some time. That waiting time is almost the spacing between 2 pi by 2 and pi pulses. At the same time, FID is gone away, but the entire thing is manifesting back to back as 2 different FIDs. That means one FID grows, another one comes back. This manifestation is called as echo. And this is what is very much famously happening. So the FID has come and gone, but this is inverted by means of a 180-degree pulse, or called as a pi pulse. So what essentially happens is everything in thermal equilibrium, you rotate it to 90 degrees by means of your 90-degree pulse. They get using this is called as evolution time. NMR people uses a different notation over here. It is being noted as tau in EPR. I think it is eta in NMR. And when they are perfectly dephased due to the spin relaxation timing. So this has to correlate with the spin relaxation timing. And then you apply your 180-degree pulse, the entire thing goes back. Then you wait until this, on the reverse of the FID happens. So instead of starting to dephase from this side, it will start to dephase from this side, and they refocus totally with the build-up of the FID and the decay of the FID. If you record the entire echo, you will end up in recording to an entire EPR spectra without much of a distortion. So this is the basics of pulse EPR, where you end up in, or generally this is called as a readout pulse. So any pulse sequence above this is built on this basic pulse sequence of a pi by 2 pi tau echo sequence is known as a readout pulse or a readout sequence. So ideally, this will end up in creating a proper FID, which is our echo itself. You have to Fourier transform that, and you have to Fourier transform it and get the spectra. Now, MIMS have found out one more thing, that this is not static. That means the height of it is not going to be static. If I extend this timing, or I start the 180-degree pulse immediately after the 90-degree pulse and slowly keep shifting at an interval, your echo is going to go up and down. This is called as modulation. That means the height of the echo will modulate like this. The place won't modulate, the height only modulate. But obviously the place of the recording will shift, because when I am shifting this is static, and I am shifting this, each of the time the place, this is accordingly, this also shifts. You have to also set the receiver in such a way that when this pulse shifts to 10 nanoseconds, the recorder also should shift in the 10 nanosecond scale. So everything shifts. Let us say in an increment of so many numbers, which obviously you require, you said during your experiment, you record the entire pulses, echoes in that period, you will end up into something like this. Instead of like this, a signal like this is observed, and this in turn is Fourier transformed properly, will give you, instead of this single line spectra, it gives you a proper two-line spectra with the center of it being the hyperfine coupling, the nuclear frequency split with the hyperfine coupling. You have a proper nuclear spectra in it. That means, to simply say on layman word, this echo modulation is equal to the nuclei which is acting over there. So obviously, when you have more than one nuclei, your modulation pattern is going to be chaotic. It is not simple. Here we are discussing only S is equal to 1 by 2, I is equal to 1 by 2. So it's, everything is simple. You have only one electron and one nuclei present, and you have only one set of modulation present in the system. Obviously, real samples, this is a very complicated affair. As you can see, the same thing happens with NMR also. Your FID of one single sample is so neat and so clean, you can even work it out with your hand. It is not possible when you have multiple nuclei present in the system. So this is an animation. So what happens after the first pulse, and after the second pulse, it is being inverted, and after that evolution time, re-evolution time, everything gathers, and then again rephases. Your recording is done from the x-axis. So since it is done in the laboratory frame, but in the laboratory recording is done in the laboratory frame, it is recorded here as an echo. So this is the origin of nuclear modulation, because many nuclei are present. When many nuclei are present, their phasing also are different, corresponding to the different hyperfine coupling present in the system. When it is coming to 3-pulse echo, it is called as a stimulated echo. It has its own advantages, because 3-pulse echo is the base of all the different regime techniques. So based on this, major experiment developed is called as electron spin echo envelope modulation spectroscopy, which was very useful in assigning the hyperfine coupling of very tiny coupled nuclei in the system. All it makes a difference is that it is using an extra pulse for tilting the entire thing into an angle, so that you have a very complex motion is available, and the echo is enhanced. So the internal middle pulse is introduced just to enhance the signal strength, or just to enhance the entire resonance mode. So what happens here is, to observe a 3-pulse echo envelope modulation. So in order to modulate this, you have to move something, right? So in order to move something, you really don't require a 5 pulse here. You only require 3 different 5/2 pulses. Here the time increment is given is here in t. This is constant. This is constant. Only thing moves is this pulse. So that you start from here, you keep moving it. When you keep moving it, this pulse will echo like that. So based on that, we have so many different experiments available to us. You have 2-pulse echo, electron spin echo envelope modulation spectroscopy, and 3-pulse electron spin echo envelope modulation spectroscopy. All these things were forgotten when we had come up with the high-score experiment, or it is called as hyperfine correlated spectroscopy. And the same thing, the beauty of these experiments was, you really don't require a RF source to record the nuclear data. Here you are recording the entire nuclear data, entire nuclear Zeeman effect, or technically you are recording the NMR spectrum of the molecule without the usage of a radio frequency, only manipulating the spin regimes. Whereas if you are using RF frequency externally, you will call the total experiment as electron nuclear double resonance spectroscopy. This is also available in continuous wave techniques. When it is continuous wave techniques, we call it as CW Endor spectroscopy. When in pulse method, we will call it as Davis Endor or Mills Endor, depending upon the technique you employ on it. And of course, as I have told you, I am not going to discuss about ELDOR, which is electron double resonance techniques. We'll slowly go into different experiment, how they look like, etc. Before going into that, what you do for analysis and interpretation is very simple. So we have different pulses moving. You have a static pulse, different pulses are moving, and you have echo modulation happening. Here it is shown as the pi/2 pulse is moving towards the pi pulse. It can be done in any way. You can keep this static and this is moved, or this is moved and this is static, depending upon that. This is the spectra of one, just with one nuclei, and the time domain analysis is same as that of as you can see, which you do in NMR spectroscopy also. So in time domain, what you do is you get a raw data, you have to fit it with an exponential decay, and then you have to subtract it using the exponential decay, and then you have to enough apodization window is applied. If you make an error over here, you will see artifacts. If you do not fill enough zero in the end, again artifacts. So see, there is a lot of backfolding. All these things are there. These are purely case of manipulating the data using your software, and then you Fourier transform it explicitly to get your frequency domain spectra. So this is the time domain spectra. This is your frequency domain spectra. This is where your nuclear modulations are seen, the same like in NMR. Of course, is that this is not an FID. This is an echo. That is the only difference between them. When it comes to Endor, what happens is, this might remind you a pulse sequence which is used in the decoupling of carbon-13, where you have a read-on for proton and a decoupler sequence, read-on for a carbon-13 and a decoupler sequence is always on. Exactly, this happens in the same way. So that means while this is recording, these three pulses are recording, you have a preparation pulse first, you prepare the entire system, and during they are under, so when they are under resonance, you irradiate the sample with an RF frequency. Here, this RF is varied from certain frequency to certain frequency. Let us say, if it is an X-band experiment, RF is varied, let us say, from 0 megahertz to 30 or 35 megahertz. You don't irradiate more than that in an X-band resonator, because X-band resonator may heat up and it will cause other troubles. So generally it is recorded over there, that period of time. So this entire thing, even if it is a huge pi pulse is applied, but pi pulse with variable frequencies in it. And after that, you have your general readout pulse, echo is recorded, and the entire echo has to be Fourier transformed to give you the. So what you are technically doing is, it is a polarization transfer experiment, same like a decoupling experiment. It is or decoupling, or you can nuclear overhauser effect. This is the same here transferred over here. That means the strength of the entire electron EPR is transferred to the nuclei, and you are polarizing the entire nuclear energy levels, and you are causing them to be under resonance. And while under resonance, only this is recorded. So when all the levels are populated, this being enhanced, and the nuclear energies can be recorded directly, measuring the nuclear frequencies. Endor measures nuclear frequency directly. ASIM techniques measures the nuclear frequencies indirectly. Pulse, this is called as a Davis Endor sequence. In a MEMS Endor sequence, it's a screenshot of the oscilloscope. Exactly what happens. This is a pi. This is a pi/2 pulse. This is a pi/2 pulse. This is a pi/2 pulse. In between, you are having a RF, and this is your echo. This is the oscilloscope view of how the pulses are acting during the time of recording. So when you are measuring the MEMS ENDOR, you have to use a different pulse sequence. Problem with MEMS ENDOR is blind spot. I'll discuss about blind spot in a minute when we are discussing high score spectra. But only your thing you have to remember is that your nuclear spectra is read out directly as far as ENDOR spectra is concerned. So you have a central hole and you have a proper line shapes in Davis ENDOR. And if it is isotropic spectra, it will look isotropic. If the tensor is anisotropic, you will get two different anisotropic tensors on both sides. All you need to do is sender is nu. If it is a weak coupling case, sender is nuclear frequency split by hyperfine coupling A parallel, A perpendicular, and A parallel, direct readout. And this is the pulse sequence generally used in ENDOR spectra. But yeah, always it is so perfect looks when it is simulated. This is the reality situation. You have a Q-band spectra of rhodium ENDOR. The frequency is microwave frequency employed is approximately in Q-band the microwave frequency is 35 gigahertz, and the RF frequency is approximately average of it is around 24 megahertz. This is the spectra. So this is the center of it, and this is the split. But obviously, you don't see these two lines in the same signal strength, because obviously due to the reasons rhodium has a very low G value, and a lot of distortions also may happen. So this is a metal center is rhodium here. This is a rhodium ENDOR recorded at Q-band, Davis ENDOR, obviously. Whereas it is, see, this is a very complicated. Rhodium is a very complicated element. Nitrogen is very straightforward. It is a N14 Davis ENDOR recorded at Q-band using copper infused porphyrin. As you can see, in three different places. This is a G parallel region. As you can see, it is so perfect isotropic. Sender is the nuclear frequency split into two by hyperfine coupling. Middle is all orientations possible, so you cannot really tell what is what. And this end is getting more complicated. But you get a pattern. It is only represented with three different spectra, but in reality, to get the entire A parallel and A perpendicular and the whole data to be perfectly fitting, people might have measured starting from here to here some 10 spectra, different 10 spectra, and overall nitrogen tensors can be calculated. What is the advantage? You can calculate the copper nitrogen distance. You can also calculate how much copper tensor angle with the nitrogen. So bond length as well as bond angles can be calculated from these experiments in reality. Whereas here it is technically impossible. So with such a spectrum, we are having unlimited possibilities. When it comes to ESIM experiment, we have equal intensities almost for ENDOR, except very rare cases. But in 2 pulse or 3 pulse ESIM, we have obviously issues with the blind spot, and as I told you, I will again tell what blind spot is in a minute. But however, we have a little bit different frequencies, some and different frequencies also appear. So ENDOR ESIM versus ESIM, one really requires a little bit of skill to elucidate the data from the ESIM techniques. So in order to avoid that all these effects, ESIM technique was more recorded by people in a two-dimensional fashion. People might think it is easy to go to 2 dimension. Yes, it is easy to go to 2 dimension. When you go from 1-dimensional proton NMR to a 2-dimensional COSY experiment, how far it is easy, only those people who have handled it will see. Remember, I mean, it is easy, but at the same time, it is trickier also when it is, especially the molecule is getting bigger and bigger. Here the thing is that you don't have all the luxury of all the protons resonating. You will have only those protons which is coupled with the electron spin will getting resonated. Generally, high score, the pulse pattern is this: you have a 90-degree pulse and 90-degree pulse again. You have one time domain which is moving. You have a secondary time domain which is also moving, that generates the second dimension. So those who have understood that 2D COSY, how the two-dimensional COSY experiment, how you are making two different dimensions using two different time evolution, the same principle applies over here. You get an echo which is two-dimensional. A two-dimensional full Fourier transform 2D to FFT will give you the spectra in 4 different quadrants. Essentially, this first quadrant and the third quadrant carry the same information. Normally, second quadrant and fourth quadrant are identical. Now, what happens? It is simple. This is how a high score data will look like, and this is exactly, there is only one quadrant, which is the first quadrant. This is a proton spectra. The center of it is exactly 15 megahertz at X band. And you see that this grid line is the center. Slightly above the center of these two grid lines, you have two lines as a contour. This is alpha and beta. So you see that, like if you can envisage two different AISO peaks, center of it being the nuclei, split by the hyperfine coupling, it is the same. Now what we see more is, we see that it is not exactly on this line. That means along this line means they are isotropic. They are slightly shifted away from that. You can, from the center of the spectra, you can take this distance. We will also get a value called as T. This is the dipolar tensor. That means how much it is anisotropic, or how much the value is anisotropic. So this is how we can from a very unclear systems, we can go for a clear readout. This is, we are highly lucky. We have only one proton which is existing over here. More than one proton, nitrogen, all will complicate the entire. I'll show you with multinuclear systems soon. So what happens with the weak coupling and strong coupling is more interesting in high score. With weak coupling cases always observed in the first quadrant. If you have strong coupling nuclei, they always appear in the second quadrant. Already this resolution will happen. So immediately when you have weak coupling and strong coupling, you will have a quadrant change from first quadrant to second quadrant. If you have quadrupolar interactions present in the system, this is the first quadrant itself. As I have told you, this is the grid line for the center of it. In the quadrupolar interactions, the lines will also split above and below that. And this distance is the P, or quadrupolar coupling constant. We can directly calculate from the spectra. So we can derive quadrupolar data. You can derive hyperfine coupling data both from high score spectra. With some simulated examples I can show you. One is a weakly coupled proton. Now only one proton. Almost complete. You can see the hyperfine coupling I've given here is almost isotropic. So it is at a center exactly at the approximately at 14 megahertz. They are exactly at the center, and it is a weakly coupled proton also. Now we are looking at rhombic tensor. You are looking at a anisotropic tensor, which is axial, purely axial system. Purely axial systems are guided by these two equations. As I have told you, this is guided by parameter T. Theta is the angle between the nuclei which makes to the unpaired electron. Obviously, these are torsional angles, and A and B are the different hyperfine coupling constants, and AISO is the isotopic hyperfine coupling. So the signed nuclear frequencies can be very easily calculated by this. The pattern will get more and more interesting when the coupling constants get higher. At the exact cancellation, you have line shape singularities occur. That means that they totally go from these type of ridges, they go to this type of observation. These are rare, obviously. And when it is coming to strong coupled proton, as I have mentioned, strong coupled proton, the center is half of the hyperfine coupling, split by 2 times the nuclear frequency. Strongly coupled protons have a totally different appearance in the measurement pattern. When it comes to rhombic hyperfine tensor, it is much more evident. This is A1, this is A2, and A3. All you need to do is correspondingly you have to read it out. But the problem is blind spots. Blind spot occurs always at a frequency of nu n is equal to n by t. That means 1 by tau for every 1 by tau nanometers, this blind spot tend to occur. What is meant by blind spot is every 1 by tau. Tau is the time between 2 different pulses. Every 1 by tau, what happens is the signal is lost. That means the entire signal should have looked like a ridge. Instead of that, we have breakages. And this shifts, of course, depending upon the tau value, there is a shift of it. For example, here the tau is 100 nanoseconds. Correspondingly, your blind spots are different. Here the tau is 200 nanoseconds. You just see the difference between the spectra. The blind spots are different. So to overcome this, Schweiger have invented matched high score. That means you match the pulses to in such a way that you get a high score spectra devoid of the blind spot. Traditionally, what you can do is record the high score spectra with same parameters, different tau values 2-3 times, and finally, after the Fourier transform, we can add all the spectra to complete the range. That is also done, but it is time consuming. But personally, we love matched high score because pulse matching that means instead of that, I'm not going into how to match the pulses. Technically, what is done is one of these pi by 2 pulse is matched with the pi pulse. So that will solve this issue of the blind spot behavior. The very same blind spot occurs in MEMS Endor also. So in the MEMS Endor, what happens is same timing problems occurs. So due to this, the blind spot behavior comes in MEMS Endor. So due to that problem, Davis Endor is most popular among people for elucidating the data. These are some real examples. One is the powder spectrum of a weakly coupled hydrogen in porphyrin sample. This is another one with a weakly coupled hydrogen as well as a strong coupled carbon 13 in the system, which is a copper unconfused porphyrin. And this is how you match the pulses. These 2 pi by 2 pulses are matched with the pi pulse with a lesser intensity and width. So this will, instead of the change of tau values, you manage it with a matched pulse, so that this will solve the blind spot behavior. This is a real example of N14 spectra of a rhodium complex. So you can see that all the 3 nitrogens here are resolved. This is a very strongly coupled. This is a d(z)² ground state. So a very strongly coupled nitrogen is N1. Then next coupling is on N2. Third is N3. So you can see that all the 3 nitrogens are visible here. Extra things visible over here are quadrupolar values. That means I can also read out the quadrupolar coupling value. This is the strongest nitrogen. I can read the quadruple coupling constant also from here. The weakest nitrogen is occurring here, and the next nitrogen is occurring here. So from a continuous wave spectra like this, I can get a spectra which is capable of elucidating all the three different nitrogen value and approximate distances along with the angles can be calculated directly from the HiSCR. This is another example with the iridium complex, where you see that the protons are not really, the protons are of these two protons. This is the iridium, these two protons on the iridium sender. They were not at all visible in HiSCR. So instead of that, we have opted for a Endor. So you see that for a complete, and here an EPR spectra look like this. So with an EPR spectra looking like that, an iridium complex with the iridium hyperfine couplings as well as proton hyperfine couplings could be very easily elucidated. They are all very strongly coupled hydrogen atoms. It can be very easily elucidated by going into a HiSCR experiment. These are some examples of, again, rhodium complexes. Here what you can see is the rhodium HiSCR. So if it has to be properly simulated, it has to look like that. But obviously due to the blind spot behavior, you can't see that. This is the rhodium signal. So these are inorganic examples. When it comes to inorganic examples, one of the best studied under pulse EPR spectroscopy is the methane production bacteria, and their or NCR coenzyme reductase is much more well studied during a time, well established and studied. So here also, at the ground state of the nickel 1 or 2 was debatable. The role of the coenzyme sulfur was debatable. So a lot of things have been elucidated by here. For example, this sulfur, all of us know that sulfur 32 has no spin. So sulfur 32, how to record sulfur 32, or whether it bonds with the cobalt or not, that was a matter of question. So when when it is under question, the sulfur 32 was replaced with the sulfur 33, but again continuous wave EPR, as you can see that the replacement has only produced a little bit of broadening over here. And people went for HiSCR analysis to find out the coupling of this properly, that the estimated that there was a very strong coupling between the sulfur and the metallic sender and nickel sender, and the metal nickel to sulfur coupling constant was quite axial in nature, with a perfect axial spectra for S33 was found out. So like that in bioinorganic samples also they work out very well. So this is another example when Q-band is matched HiSCR, you do not have blind spots, beautifully clear elucidated spectra are observed. Some experiment on copper 2 complexes of N-confused porphyrins. Again, this is carbon 13 data, and this is the data coming of, again, carbon 13 of directly bonded copper and carbon of the N-confused porphyrin. Professor Schweiger has gone to the extent of on real-time samples. For example, if you look at some of the rhodium complexes, it was not even possible to resolve the data properly. So this was one example. In fact, these are two examples we have done way back by using hyperfine correlated Endor spectroscopy. This is a two-dimensional Endor where you incorporate two different RF pulses, like very same, or if I want to equate it to NMR, HiSCR is almost like OC. This is like HMQC. So here you have very good resolution of one side hyperfine coupling, other side is the nuclear frequency data. In weak coupling, they look different. In strongly coupled cases, they look different. They work very well with the biological samples. They work very well with inorganic samples. They work very well with organometallic samples. These are three different examples. This is a rhodium complex with a proton on a weak coupled regime for this experiment. Strongly coupled N14 in myoglobin. You can even see that. See, there are 4 lines coming from the myoglobin. This is one nitrogen, same nitrogen. This distance is their quadrupolar value. So the quadrupolar, and this is their hyperfine coupling value. Quadrupolar and hyperfine coupling are direct readout from here. This is an example with rhodium and carbon-13. With this sample, it was impossible to observe the carbon-13 even with high score or Endor. We had to go to this experiment. Obviously, this experiment took more than 24 hours to perform to get to such a level of spectra. But crazy things, yes, always exist in pulse CPR also. This is one of the craziest of the experiment. Yet another crazy experiment which was devised, I think I have never seen it in use afterwards. It is called as electron Zeeman resolved EPR, where you can resolve the electron Zeeman effect in 2 dimensions. Advantage is you mix copper complex with vanadium complex or copper complex with iron complex. Copper complex, any 2 different or 3 different complexes are mixed, given to you. You are asked to take a spectra. You can resolve it in 2 different dimensions. One in terms of magnetic field, other one in terms of G value. You can very clearly resolve it in 2 dimensions, called as electron Zeeman resolved EPR spectroscopy. So for reading, a recent book has come up with Stefan Stoll, who is a student, was a student of Professor Schweiger, and a very famous Professor Daniela Goldfarb from Israel. Honors here in EPR spectroscopy fundamentals and methods, a beautiful textbook which has recently appeared. But the focus of the entire techniques have gone from these biological or inorganic samples to completely to spin paired systems or spin labeled systems, distance measurements, etc. So unfortunately, many people do not work in inorganic chemistry or exploit it in inorganic chemistry. Like Professor Rohit John has asked one question, that what are the cases may find pulse CPR more applicable. Actually, as an inorganic chemist, if you are having pulse CPR machine with you, it is highly useful in elucidating the active centers in when we are going for, like, let us say, cytotoxicity, etc. How this acts with real samples, that such type of studies could be performed. But obviously, you really require a huge facility to perform that. But without much of an issue, active centers and their structure to activity correlations could be easily studied with given techniques or a combination of given techniques, and could be understood. Biological samples works very well. Organometallic samples work very well. Only thing is that provided you have to prepare the sample properly. So I take this opportunity to thank the Magnetic Resonance Society of Kerala for inviting me and probably making me to do some homework of a forgotten topic also for a longer time, because here in NIT I don't teach spectroscopy anymore. For the last 4 or 5 years I've been only teaching inorganic chemistry. So it was kind of a completely forgotten topic for me. So thank you very much once again for your time.
Thank you, Dr. Sriga. Maybe you can take some questions, right?
Yes, obviously.
Participant, you can post your question here. You already answered John's question, right?
Yes.
Okay. I don't see any more questions. So
may I ask a very naive question?
Yes, sir.
In some context, you mentioned the word confused something.
Yes.
What's the technical meaning of that?
in porphyrin, we have 4 nitrogens in the core of the porphyrin. So when you synthesize that, if you can confuse one of the nitrogen with the carbon, it is called as N-confused porphyrin. That completely changes the ground state of the molecule. That goes from a normal inorganic complex to it will go to an organometallic complex. That means the pyrrole, one of the pyrrole, just it just flips. That the carbon bonds with the metal. So it is called as N-confused porphyrin.
Okay.
With a direct metal carbon sigma bond, which is very rare. And what is observed that time was it completely messes up with the ground state of the metal.
I see. Okay.
Yeah. Because it doesn't. Normally, these 4 nitrogen atoms are same. And it is in the copper porphyrin, the 4 nitrogen atoms are same. The moment it is one of the nitrogen is changed to carbon, then the ground state no longer lies along the dx square minus y square ground state, and the spin density completely is messed up. So we have done some studies in cobalt and copper, and we tried to extend to rhodium, but somehow we didn't. Unfortunately, we demised that time, so we couldn't work much on that. But I think if you remember, the high-end spectra was my most beautiful day when we recorded the high-end. It was very difficult. Until that time, we never tried it in real samples. And they always had recorded the high-end in these cold samples, not in real-time samples. But it works beautifully in myoglobin or in organometallic complex. Yes, it works perfectly. But to set up an EPR laboratory, that is another case. It doesn't happen.
Thank you.
I think there's no more questions.
So, Arun sir, I have some announcements before the conclusion.
Okay, just before that, thank you, Dr. Srikanth, for delivering this wonderful talk, and probably we will get in touch with you for next programs. Thank you so much. Okay, Dr. Sunil, please.
Yeah. I have some announcements regarding this webinar before concluding. So, on behalf of Magnetic Resonance Society Kerala, I would like to thank all the speakers and all the participants for making it a grand success. We expect all the support in future also. So in the chat box, I have posted the link of a feedback form, and please fill in. I will send the same through email also to all the participants, and you do it in 1 or 2 days. And also we will send you the participation certificate in 1 week after the lockdown, because we have to go back to the workplace for preparing these certificates. So after the lockdown, we will go to the workplace and prepare, and in 1 week after the lockdown, we will send you the participation certificates, and we will consider the attendance, your participation also. The Google Meet already automatically recorded your attendance, so we will consider for giving the participation certificate, and also consider the feedback also. And most of the participants are members of Magnetic Resonance Society Kerala. If someone is not a member, and please join Magnetic Resonance Society as a member, and I will send the application form also along by email. So thank you all, and please conclude, Dr. Arun sir. Yeah. Thank you all again.
Okay.
Thank you and bye-bye.
Hello. Am I audible?
Yeah.
Okay. So finally, we have come to the end of the program. It has been very exciting in all these 4 days, spending time with pioneers in magnetic resonance spectroscopy. We have covered different areas of magnetic resonance spectroscopy, its theory, instrumentation, and applications. We have seen the basic principles of NMR, EPR, its applications in chemistry, physics, and medical fields. These topics are handled by experts in their respective fields and all are from very premier institutions in our country. Needless to say that we are all highly benefited by their talk. I thank every one of them and we look forward to hearing your classes in future too. We have recorded all the speeches and we will soon be available to the students for your future reference. Let me thank Dr. Sunil Kumar and Dr. Vijesh Vijayan for selecting the best speakers, and I'm sure that participants are highly benefited. SRIPS is one of the R&D institutions under Kerala State Council for Science and Technology, which is organizing many similar capacity building programs. And in association with the Magnet Resonance Society Kerala, we will be organizing many more programs like this. So I request you all to get touch with us for getting in. SRIPS will be having colloquium on different topics in addition to NMR and magnet resonance. We will have different topics also for colloquium. And hopefully by next month, we will have a webinar on light and matter interaction. So students who are interested may join. Before concluding, let me thank once again the speakers, the chairs of various sessions and participants. Stay safe. Thank you.
Thank you all.
Thank you.
Thank you, sir.
Thank you.
I think with this
Thank
we
you
will
very much.
conclude the session.
Yeah.
Thank you. Thank you,
you all.
Srikant. Great
Yeah,
talk.
thank you, Professor.
Thank you.
Okay, Professor Bhatt, we will discuss about this APS meeting in the executive
Yes,
committee
yes.
meeting, and we will
Yeah.
let you know in 1 or 2 weeks.
Right,
Okay.
right. Roughly now it's once in 2 years.
Yeah.
So after this year's meeting in China,
Yeah.
India's one will come in 2023.
Yeah.
So we can plan for that. There is enough time for planning for that.
Yeah, thank you very much. Thank you. So,
Thank you,
shall
Sunil,
we
Vijesh.
conclude?
Yeah.
Yeah.
Yeah. Thank you so much. We will have
Thank you.
more webinars there
Yeah,
in
yeah.
future also.
Bye-bye.
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 Bye.
Stay safe.
Stay safe. Yeah.
Bye.